Okay, we're back. We lost a few people already, so it's an interesting trend. That's going to continue throughout the year, I'm afraid. So I'm going to go through a few applications just to give you an idea of the variety of things you can do with data mining. Without actually understanding data mining yet to full detail, but I think you'll be able to appreciate that. So here's one of the recent projects. So most of you are Dutch. So if you're Dutch, you know how important speed skating is. In the Netherlands at least. Not in the rest of the world, but in the Netherlands. So we had the fortune to be able to work with the biggest Dutch speed skating team called Lotto NL Jumbo. They're also the biggest, well, by biggest I mean the best speed skating team in the world. That's simply because only Dutch people do speed skating and they win pretty much everything. So here's when I visited the training camp with them. So Lotto NL Jumbo, for those of you who follow skating a little bit. Sven Kramer, Kjeld Nuis, those kind of, in Dutch at least, world famous people. They are in this team. The nice thing about this team, other than that, is that the coach collects a lot of detailed data about how they train. So on a daily basis, they record everything they do, how intense was it, what exercise did you do, and so on. And of course, then you have race results, and those are the outcome, pretty much, of all the preparation that you do. So these people train 6 days a week, and they train twice a day. So these are true professionals. So that if you do that for 15 years, you get a lot of data, and we have an interesting data set based on that. So when I spoke to the coach, he said something simple. Well, here is a lot of data. Just tell me something that I don't know yet, which is kind of a challenge, but yeah, it was a fun challenge. And we taught him a few things that he didn't know yet. He's also been around for 15 years, of course, and he has a big data mining thing in his head. But still, we were able to show him some novelty. Right, so of course they want to know about training, right? So what are some properties of effective training? So it's very easy to train a lot, but it doesn't always mean that you get stronger or you get faster or healthier. So it's actually a fine balance between training and recuperation and rest, pretty much. And the nice thing about these people is that the only thing they do is train, rest, and eat, pretty much. So they're like machines, and these machines produce data, and we analyze them. And because they're machines, there's some regularity in there, and that's what makes it easy for us. Well, not easy maybe, but doable. So here's a guy called Kjeld Nuis. He's been very successful, and earlier this year he won 2 Olympic medals, gold medals even, in the 1,000 meter and 1,500 meters, so these are kind of medium distance. He's called a sprinter, which means that sprinters are able to produce a lot of energy in a very short moment. But if you have to do it for more than a minute, then it's already starts to deteriorate. So Kjeld Nuis is a sprinter, and if you know these people, Sven Kramer is a long distance skater who excels. He doesn't excel in sprinting, but he excels in 15 minutes of intensity. So in the year that we did this analysis, we did the analysis just before the season, the winter season, when there's ice. And in that season, he won quite a few medals and so on. And you know, who knows? Potentially, that might have been a little bit due to the advice that we gave on how to prepare for a race. So, of all the different things that we looked at, here's just a very simple, accessible, I hope, pattern that we found. So, this guy, Kjeld, at the time that we were analyzing it, we had some 100 examples of races that he ran. So for every race, you could look at the result, right? But also whatever he did in preparation for that race. So we took about 4 weeks of the training data before the race, and we tried to figure out if there's anything in there that you could notice that either predicted a good result or a bad result. So if you listen to athletes on TV after a race, they always say, well, I had a good day today or a bad day today. And they always think it's some kind of magical thing in their body that they cannot grasp. And we always think, well, it's in there, it's in the data, but you just have to look a bit carefully. We analyzed a few hundred different attributes, different variables on how you train. So how you train is a very multidimensional thing. I mean, one dimension would be, okay, how intense is the whole thing? How much training do you do? But it's not that simple. It's also about how much do you do on the day before the race? How much do you do on the 3 days before the race? On the 5 days? On the 20 days? How much do you do in the mornings? How much do you do of weightlifting versus maybe cycling or actually stuff on the ice or maybe on inline skates? So there's a lot of details that you can pull out of this training data that give an indication of some aspect of training, but we don't know which of these aspects are the most predictive. And that's the major challenge here, to somehow pull out that attribute that is predictive. So one of the most predictive ones, still a bit noisy, but of interest at least, is this variable here, which says the sum of the load of the morning trainings over the last 5 days before the race. So the load is actually something computed by, you take the number of minutes of training and you multiply that by the intensity. So if you have a very heavy training and you do it a long time, then there's a lot of load on your body, which might be good, might be bad, don't know. And then the sum of that over 5 days, that's some variable, but in this case, specifically, you're only looking at the morning activity. Now later on they told me, well, that's interesting because in the mornings we actually train on the ice and in the afternoons we train in the gym. So actually it makes sense that whatever you do in the mornings is somehow different from what you do in the afternoons. So what do we have here on the axis? So this is the sum of the load of its specific characteristics. And apparently if you have a high load, in this case 200 intensity minutes, I think the scale. That means that your relative time, and that's a way of somehow comparing different races in different environments. I'll skip the details. But it means that you were in the values of 1.04, which essentially means 4% above the track record. So 1.0 here at the bottom, that means you're on the level of the track record. So you're one of the fastest, or maybe even the fastest people ever to race this kind of ice. And if you're 4% slower, that means that you're just, you're not winning any medals at that point. So when so every dot here is a race. So if they had a race and they didn't know about this variable, they would just say, well, I was 3% slower, but somehow I didn't have a good day. But here is some explanation of that. Well, you didn't have a good day because actually in the last 5 days in the morning you did too much. You came at the race too tired. So it's kind of a negative result in the sense of if you train too much, your results will be bad. Now you can imagine that if you do zero training, that's not good either. So somewhere here on the left there's 0. Probably this graph here will go up again. If you do no training at all, you're probably not going to win any races. But apparently these guys overdid it. There's an optimum somewhere in the middle, but they did too much training. They were too eager, essentially. They thought, I'm not going to sit in my chair for 5 days. I need to be prepared, I need to train and so on. But they just got just a tiny little bit tired. They didn't realize it, but they lost a few percent. You shouldn't do that. So the coach immediately introduced a limit. He says, okay, I'm going to check the schedule, whatever I've scheduled for the next 5 days. In 5 days I have a race. I'm going to check whether that number is here somewhere below that line, and then it's good. If it's too high, I'm going to reduce the load on my pupils. And that might have worked. We won quite a few medals. we're still working with these people actually, so there's always more data, more stuff to analyze. This is a different project on a highway bridge that totally different setting. This is a big highway bridge between Amsterdam and Almere, and it was closed at some time, and because it was deemed unsafe. And when it was renovated, they introduced all kinds of sensors in the concrete to measure the bridge, and hopefully to get a feel for what happens to a bridge when it starts to deteriorate. They kind of overdid it a little bit. They spent $500,000 on sensors and on the system and hardware and everything. But got a very nice data set out of it, producing 5 gigabytes of data, and it's actually still collecting, so it's round-the-clock measurements. So they put in 145 sensors of different types, and they put them in different locations, inside the asphalt and underneath the bridge, and in the wind, and in the outside of the wind, in the sunlight, and so on, to look at all kinds of different aspects of this bridge. And well, we spent 4 years analyzing this data and trying to pull out all kinds of interesting facts. But here's just an example that I want to give you. We're looking for kind of recurring events in this data set. It's a very long timeline, essentially. It's a time series, 145 time series actually put together. And we were looking for recurring events, so kind of patterns that you see in the data. Oh, here's that pattern again. But then also on different time scales. So you could look at maybe stuff that happens every day, or stuff that happens every hour, or every minute, or every second even. I mean, there were all these different levels. So we were measuring 100 times per second. So you could go from, let's say, the level of months, all the way down to 100th of a second. And here you see 2 examples. So one pattern is the top one there. That's actually the pattern that we call a sunny day. So here's a bridge. You measure how stiff the bridge is. Actually, if it's a sunny day, then the bridge heats up because of the sunlight, and the bridge gets a little bit less stiff. So it sags a little bit, and that's actually the measurement that you see here. So you see the red lines in the top graph. Each line is approximately, let's say, 20 hours. So you can count the number of days here, and there were some sunny days and there were some cloudy days. And you can see kind of a global trend. That's just the temperature, the outside temperature. But on sunny days, you get a lot of radiation on the bridge, and actually the bridge is much warmer than the outside air. So you see this pattern, and you know you can see the daily rhythm, but you can also get a feeling of the weather that was going on. On a totally different time scale is the event that you have over here. So these are actually 20, means you have to divide by 10 because these were 10 measurements per second for simplicity. So that's 2 seconds. Anybody knows what that pattern is?
Car, maybe.
Says car?
A car driving over the bridge.
Yeah, well, it's actually a truck, but yeah, similar. So if you have a truck on the bridge, it will take about 4 minutes to pass this segment of the bridge that we were recording. Sorry, 4 seconds. So from minus 20 to 20. A truck is heavy, starts to sit on the bridge sags a bit more, you measure this in the data. And all of the red dots are occurrences of this event. Well, there's thousands of occurrences, of course. So you see these all over the place. If you zoom in a little bit, you notice that they don't happen so much at night. But they happen on sunny days, they happen on cloudy days, they happen at night, and so on. So these are kind of events that are superimposed on each other. Even if the bridge is sagging, you still get a truck over it. If you get a traffic jam, you can still have a truck in a different direction, so all of these things are superimposed. Which made for a very fun project, actually. Right, this is probably the last example I'll give. Well, we'll see about that. So, very early on in my career, I did a project with KLM. So KLM, they have planes, of course, that they exploit. and planes have to come in every few months for maintenance. Now, when you have a plane coming in for 2 weeks maintenance and checks and everything is fixed again, it's very expensive if you don't have the right parts in those 2 weeks, because the plane will be down, and any day that the plane is not flying, it's going to cost you a lot of money because you cannot transport people. So it's kind of nice to know on the day that the plane arrives in the hangar that which parts you're going to use. And there's about 10,000 potential individual parts that you could have to replace. So it's very nice if you can somehow predict what's going to happen if you're going to check them. And there are all kinds of variables on how did you use the plane over the last months. So if you always fly over the North Pole, that's a different thing than if you always fly to London and you have 5 different hops on a daily basis. So if you do a lot of hops, you get a lot of landings, a lot of takeoffs, that's going to give wear and tear on a different part of the plane than when you fly over the North Pole or over the Sahara. So that's interesting information, and also, of course, what are you actually going to check? If you're not going to check component X, then probably you're not going to use part Y, because that's only replaced when it's checked. This is, of course, a little bit of an unsafe feeling that the plane is always flying with stuff that's wrong with it. Just as your car essentially always has some things with it, but you still fly with it. I think on average every plane flies with about 10 defects. But a defect could be like a little sticker on the toilet that's missing, so no smoking sticker or something like that. So it's okay. KLM is okay. Right. So one option, of course, would be to say, okay, I don't know which parts I'm going to use. I'm just going to keep a spare plane in my stock, and whenever I need something, I know that it's there. I'm just going to take it and put it on the plane. Now that's fairly expensive, of course. So ideally you have something in the middle which says, I don't know exactly, but probably I can predict it, and I can get some stuff that, if it's cheap and probabilities are fairly high that I need it, then I'll just keep it on stock. If it's very expensive and probabilities are very low, then I'm just going to check them in the beginning of the week, and then I'm going to order it, and it takes a few days to get it. So in theory, if there's 10,000 individual parts, then you'll have 10,000 individual predictions, right? So each part separately, you need to decide, is this going to be used over the next 2 weeks or not? So that's, I don't know if there's some, that's kind of the idea that we have here. So in the end, it turned out that not so many parts were very predictable, so it was not a huge success, the project, but still it was a fun exercise, one of the first projects that I did. So think back of the paradigms that we saw in the beginning. So we had supervised versus unsupervised. If it's supervised, we had classification or regression. If it's unsupervised, we have clustering, association. So is this supervised or unsupervised? What do you say? Does anybody want to give it a try? Is this supervised or an unsupervised system? Can I see some hands? Who wants to try it?
I'd say supervised, because you know what you want to learn. That's which part you're going to replace.
Right. So you have a specific part that you're interested in.
You could say that it's unsupervised because you don't know which part you can predict.
Right. Yeah. Okay. Anybody have a different opinion? You had a hand?
I think it's supervised because you want to know if you have to record the part or if you don't have to record the part.
Right. Okay. But there's multiple parts, right? Yeah.
I would say clustering, so unsupervised on the base of flight, what you're going to do. So like if it's a long flight, then that's a kind of a group, and short flight and that kind of stuff.
Right. So you can cluster the planes that have long distance flights and the short distance planes. And yeah, it's okay, fair enough. Anybody, so that's unsupervised, right? Clustering is unsupervised. Anybody else who thinks unsupervised? No, maybe we should just make it democratic. So who thinks this is supervised? Right? Okay, it's less than 50%, I would say. Who thinks it's, what did I ask? Unsupervised? Supervised. Okay, thank you. Who thinks it's unsupervised? Fewer people. Who thinks it's a third option other than supervised or unsupervised? Oh, yeah, a third option? Yeah.
I think you started with unsupervised, so you first make some clusters.
Ah, that was your idea, right?
And then you change it into a binary variable, ordering the
Okay.
data.
Yeah, okay, fair enough. So people who didn't raise a hand, they were just unsure, right? They didn't know. Yeah. Okay. Okay, so it's I would say this is supervised for the moment. So let's say it's supervised. Is it then is it classification or regression? Who thinks it's classification? Who thinks it's regression? Okay. Why is it classification? You.
Yeah, the kind of stuff that is going wrong. So the kind of the particles that are going wrong that are the classification of what kind of stuff is going wrong with the plane. When it has
Yeah, okay-ish answer. Anybody has a different answer? Better, ideally?
Either you replace it or you don't. So it's a binary variable. So
Right. Yeah, that's a good point. But we have 10,000 parts, right?
just look at them individually.
Okay. Yeah. Well, that's actually the right answer. Very good. So there's many ways of looking at this, but I think the most obvious one is that it's a classification problem, but it's a repeated classification problem. Actually, it's 10,000 classification problems with the same attributes in terms of flight history and maintenance and so on. But in each case, you're picking another target attribute. So in this case, you have a whole bunch of attributes about what you did to the plane, and then 10,000 attributes for the parts. And each of those is a potential target where you're looking to predict each one of those. Either you need to get the part in stock, or you don't, based on the flight history. So that makes a classification, it's binary classification, so it's yes or no, but it's repeated. That's what makes it a little bit confusing. One answer could have been association. One reasonable answer. Who would have thought association? Yeah, of course. Now it's easy, yeah? Association. Yeah, you said association as well? Do you want to motivate? Why?
There's probably a pattern to be recognized in all of the different parts that all those planes have, so you can't do it through the association rules. You could make maybe some clusters even, or at least a pattern that you can find which parts often have to be replaced together or something like that.
Yeah, okay. Who had the other, yeah, do you want to?
I figure that when you replace one part, you also have to replace another. And maybe on certain flights, long distance flights or short range flights, you have to replace certain parts multiple times.
Yeah. Yeah, so the idea here is that the parts are like the French cheese and the red wine in a shop, right? Supermarket. The idea is that if you're going to replace part X1, you're probably also going to replace part X2 because they're connected to each other. So in this case, you can look for associations between these different parts that need to be replaced. If you're replacing this one, you're always replacing that one. Or maybe vice versa. If you're replacing this, then you don't need to replace the other one. But in this setting, you would leave out the maintenance history. That's the only downside of this approach. So it makes sense, but in this case, you're ignoring the flight history and the maintenance history, which is an opportunity that you're missing out on. Then. So I would say this is mostly supervised. This is mostly classification, as I said before, but there are some association sides to it. The person who said clustering also has a point actually, because you could argue that regardless of what parts I need to order, I can cluster my planes into different categories, and then when I know the different categories, then I can start to reason about, okay, if I fly over the North Pole, then I probably need to replace the de-icing, blah, 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 something. So, in a given applied project with enough complexity, there's different data mining opportunities that you can find, and typically they will have different data mining paradigms also. So from now on, we'll probably only analyze fairly simple problems where it's clear, okay, this is classification, or this is regression, but in practice you will find mixtures of these things. So keep that in mind. There's one more example in the slides, but we don't have time for that. So have a look at that. It's actually, yeah, okay, it's in the slides. It's not in the video. Sorry. And if you're interested in a few more of the projects that we're doing at LIACS, then here's a few examples as well. Okay, so I won't see you next week, because next week no lecture. I'll see you in 2 weeks in this room.